linear equations. No matter how many equations and variables there are in our systems of linear equations, there are three scenarios that can happen. The first one is that there's exactly one solution, and that's called consistent, like a mathy word for that. It's consistent, meaning it has answers, and independent. Independent meaning it goes its own way, except for that one spot where they go together. Okay. The second scenario that could happen would be that you have infinitely many solutions. And that would be consistent. Consistent just means I have answers or an answer. And then instead of independent, because it's infinitely many, they are dependent. You'll hear me say one solution, infinitely many solutions most of the time, but I bring up the other word because sometimes they'll throw those in on the final exam. They'll put a problem up there and they'll say, which of these systems is consistent and independent? And you'll have to find which one has one solution is what that means. So tie those words together. And then the third scenario is the fact that you have actually no solutions. And if consistent means you have answers, inconsistent is the antonym of that. So that means you have no answers. Just inconsistent system has no solutions out of that. So with linear systems, what we're talking about are either straight lines or flat planes. When we're dealing with two-dimensional, we're talking about a straight line, two straight lines. If there's one solution, it's two straight lines that cross. If there's infinitely many solutions, it's two straight lines that land right on top of one another. If there's no solution, it's two parallel lines. That's what it looks like as far as graphs go, if you looked at the graph. So one solution, you're looking at an intersection. Infinitely many solutions, same line, and no solution, think parallel lines. Now, several ways to solve these systems of equations. I'm going to show you how to do it using matrices and the calculator as the primary way of solving these systems, which I think is the most efficient way of doing that. So let's just look at an example, or 10 or so. I can't remember how many. It's several. Let's look at a couple of examples and learn how to set them up in those matrices and solve. All right, so with systems of equations and linear equations at that, if we're going to solve it using this matrix method with the calculator, we need them to have the x and the y on the same side. And we would, in an algebra class, we normally call that standard form. Just meaning x and y on the same side. And we usually want x's first, then y's, and then it's equal to some number out of that. So when you have that, you can set up what's called an augmented matrix. And it looks like this. You take the coefficients in front of the variables, 1, 4, and then what it's equal to is 14. And then the second row is 3, -2, and then 0. The size of that matrix is 2 by 3. It's got 2 rows and 3 columns. That's how you determine the size. You got to know the size so that you can get your calculator to emulate that matrix. So what we're going to do is we're going to take this matrix and we're going to do reduced row echelon form. Reduced row echelon form was created by this pair of people. One guy's last name was Gauss, and the other one was Jordan, not Michael Jordan, but maybe different Jordan. Anyway, reduced row echelon form. I'm highlighting first letter because that's what we're going to have to look for on the calculator is RREF. Okay. So the first thing we want to do is put this into our calculator in that form. So on your calculator, you're going to hit second, and then right there below the math button is the inverse button, but above it, it says matrix in blue. So second x inverse should get you to this page. It looks something like that. All right. And we need to edit because we've got to put in our matrix that we have here. Not likely that the right one is in there. So press over to edit, and I'm just going to pick matrix A. And then the first thing it asks me is what size is your matrix? And ours is a 2-row by 3-column. So we want to put 2, enter, 3, enter if it's not already that size. And then it should show you a matrix underneath there that's exactly the right size. Okay? Then we're just going to put those rows in there just like what we wrote down. 1, 4, 14. So 1, enter, 4, enter, 14, enter. Then the second row was 3, 3, -2, and 0. And you can't like clear one out. You have to just basically type over whatever's in there and it'll work there. So make sure you've got before you leave that spot, always just make sure all your signs are correct and everything's in the right spot. Because if you just miss a sign, it's going to completely change your problem and not get you the right answer out of that. And since we're not doing a whole lot of handwork here, not many places to catch it out of that. So just be very mindful of details here. All right, so once you've gotten the matrix in there, you want to get your calculator to do that reduce row echelon form. So what you want to do is hit second mode just to get back to the regular calculator screen. That's the quit function. And then we're going to hit second matrix again. And this time we want the calculator to do some work on that. So we're going to go to the math menu. And we're going to scroll until we find RREF, which should be toward the bottom somewhere. There's REF, and then RREF is the next one. You want RREF. REF doesn't go with a full finished product out of it. It just gets us part of the way. So RREF is what we want to select. So I press enter, and then it asks, okay, well, what do you want to do that to? So we want to tell it to do that to the matrix we put in. So I'm going to hit second matrix. I put mine in matrix A, so I'm just going to hit enter there. You can close the parentheses if you want to. You don't have to. Just hit enter. And it cranks out a 2x3 matrix that looks like that. So I'm going to write that down. 1, 0, 2, 0, 1, 3. What that says excuse me, is that this row, remember when we put in our matrix, what was it, the things in this column here from our equations? This column was x plus, and then 4 was the y. This column was 3x and then -2y. So anything in this column is about x's. So this says 1x plus 0y is equal to 2. So that just is a way of saying x is equal to 2. So we get our x value is 2. Our y value comes from the second row. 0 x's, 1 y is 3. So y is equal to 3. We can get an ordered pair for that. 2, 3. That's how we normally will see our answers, as an ordered pair. When we do 3 variable systems, it'll be like an ordered triple out of that. But it really is that easy. If you took an Algebra 1 class or Algebra 2, we do this stuff. A lot of times we'll make you do like substitution or elimination. You may remember doing that, where you would multiply this equation by 2 and change it into 6x minus 4y is equal to 0. And then you would add the 2 equations together. And those 2 together would give me 7x. The y's cancel out, and that's equal to 14. And if you divide by 7, what does x equal? still equals 2, just like I got from just doing the matrix thing. This one's a little easier to do that with because it's real small. When you get bigger numbers or even fractions in there, it makes it tougher. But the reduced row echelon form thing works every time. Okay, it's gonna crank out our answer there. Let's look at a larger system that has 3 variables, which is where this method really shines, because the other methods for doing 3 variables, well, as my son says, they're stinky. They are not very fun. And no, don't turn me into DCS for making my 8-year-old do math. I know it's mean, but he actually likes it a lot. We don't do algebra yet. We're working on it. All right, so before we can start and put it into our matrix, we've got to make sure it's in the right order and the right format. And just like the first example where we had X's and Y's, we needed those on the same side and then plain numbers on the other. This one's the same way. We need X's, Y's, and Z's all on the same side, and then the plain numbers on the other. So we need to rearrange this one a little bit. The second and third equations are kind of messed up. So I'm going to move the 1 by addition, and that'll give me X plus Z equals 1. And this one will be X plus 2Y is equal to -8. And all I'm doing is just organizing myself so that it almost looks like a matrix right now before I go to put it in my calculator out of that. So when I go to put that in my calculator, and it usually, I won't say that you'll need to write this down every time, but I like to write it down the first few times I'm doing it just to make sure I've got everything in the right spot. That first column is X's, second column is Y's, the third column is going to be Z's, and the fourth column is going to be what those equations are equal to. So just make sure you organize yourself there. And then the second row would be 1, 0, 1, 1. And the third row would be 1, 2, 0, 8. I messed up on the sign on my equation there, because that was a -8 there. It should be a +8 on that side. Okay, and so that's a good reason to write it down there. I've already messed one up. Now, what size is that matrix? How many rows are there? 3 rows. How many columns? 4. Okay, so we're going to have a 3 by 4 matrix that we need to do RREF to. Second matrix, go over to edit, pick a matrix. I'm just going to use A again because it's there, and 3 by 4. And when I hit enter, it rearranges that to it's a bigger matrix. And then I'm just going to put that stuff in there. 2, enter, 1, +1, 0, 1, 0, 0, 1, 1, 2, 0, -8. Okay, got that in there, and then I'm going to do the same thing that I've done before. Second matrix, go over to math, pick up RREF, and tell it what matrix that I put that in. And here's the beautiful thing is, we get decimals here, but that we don't usually make sure I type that in right. 1, 2. I did the same mistake. It's a +8. What happened, David? All right, here's a good lesson. You can press up and grab that and just hit enter, and it'll copy and paste it. And since I've changed what's in that matrix, it only knows what the new one is now. And I get 2, 3, -1 out of that. Not to say that you won't ever get fractions as answers. You will. So this one, you have x is equal to 2, y is equal to 3, z is equal to -1. So you get this order triple, 2, 3, -1, x, y, z. That's what those are, or x, y, and z. Top row gets you x, bottom row, or second row gets you y, third row gets you z. If you had a 4-variable system, you should have a 4x5 matrix, and you would have 4 answers there. Each row being, top row being x or w, second row x, third row y, last row z. Out of that, that's how. But it's just really straightforward in how to get that solution there. Let's look at some of the exceptional ones. So these two, example A and B, had one solution. They were consistent and independent systems. The 2-variable systems, I said, was on one line crossing. A 3-variable system that has one solution. A great example of that is like the wall, the ceiling, and that other wall. When they meet up in that little corner up there. Is one point. Is the only place where this wall, this ceiling, and that wall meet. Is one point. That's an example of where that's happening at. So 3-variable systems, you can have one solution, and 2-variable systems, you can have one solution out of it, but they're all linear. Let's look at example C, and we're going to look at some of them that are the different choices out of that. So let's do this one. 6x minus y minus z equals 4. Negative 12x plus 2y plus 2z equals -8. 5x plus y minus z equals 3. Okay. So again, we're going to have a 3x4 system. 6, -1, -1, 4, -12, 2, 2, -8, 5, 1, -1, 3. So we need to put that matrix into our calculator. 3x4 matrix. Second matrix. 3x4. 6, -1, -1, 4, -12, 2, 2, -8, 5, 1, -1, 3. Second quit. I'm used matrix A again, so I'm just going to pull that. And here I got decimals in there, which is quite okay. I'm going to hit math, enter to change them into fractions. Just the same way you would a regular number. And it also makes that a little bit easier to read. And that bottom row is kind of weird looking. Look at the bottom row of that matrix. It has 0, 0, 0, 0. Everybody's a 0. It says 0 x's plus 0 y's plus 0 z's is equal to 0. And then notice that up here, these are not zeros like they normally should be. We're doing reduced row echelon form. So this is an exceptional problem. That bottom row having all zeros on it, what that tells us is this has infinitely many solutions. Okay, infinitely many solutions means this one's consistent and dependent. So with a 3-variable system, a physical example of something that has infinite number of solutions would be if you had this wall, the ceiling, and another copy of this wall. The line that's created where the wall meets the ceiling maybe is maybe the other side of this wall. Like that's 3-dimensional. the other side of this wall with the ceiling, and then this side of the wall, they all meet at that one spot, that line that runs along the ceiling. Okay, so that's one example of this. Another example would be like if you had two planes that just sandwiched on top of each other, or three planes that sandwiched on top of each other. That's a good example of those. Now, with infinitely many solutions, with three variable systems, we need to be able to write our solutions in the form of one of the variables. And the most common thing is to write the solutions in the form of Z. I'll show you how to do that. This is not too difficult, but it's a little bit weird. All right. So what happens here is you've got in these two lines here in the matrix, you've got equations that you can pull back out of there. That top row gets us this equation x minus 2 over 11 z is equal to 7 over 11. I can get x by itself really easily, right? And that would say, I would just add 2 over 11z. And that gives me x equals 2 over 11z plus 7 over 11. That gets me x by itself and gets x in the form of z because there's no other letters in that side other than z. The second row gets me the equation y minus 1 over 11z equals negative 2 over 11. I could take that and get y by itself by just adding 1 over 11z. So I'd have 1 over 11z minus 2 over 11. And that's y. So the ordered triple for this one, and this is the weird part where everybody kind of goes, what? You get x and y by itself. And then you write the ordered triple, 2 over 11z plus 7 over 11. That goes in the x spot. In the y spot, you're going to write 1 over 11z minus 2 over 11. And in the z spot, since we're writing it in the form of z, you just put z. And that is the ordered triple that is the solutions to that. What that means is if you're writing it in the form of z, z should be on the only variable in what's left. If they said write it in the form of x, then x should be on the only variable that's left. Z is the most common one that you'll see in this class, or pretty much every class that I had. We did linear systems in. We did Z most of the time. The exception would be when the system really didn't have any Z's in the leftover equations. That didn't happen very often at all, and that was like way on up in linear algebra before that happened. So, but anyway, just be able to get Z by itself or the X and the Y by itself with the Z in there. That gets you the infinitely many solutions, and we're going to be able to write it like that on the answer choices. Which is kind of weird. All right, so the key to knowing infinitely many solutions with the matrix is that bottom row. If the bottom row is all zeros, it's infinitely many solutions. Okay, so that gives you the clue that that's happening. Bottom row is all zeros. That's the infinitely many solutions. Let's look at example D. X plus Y plus Z equals 6. 2x minus y minus z is equal to 3. X plus 2y plus 2z is equal to 0. So we got a three variable system here, and we're going to take that and try to solve it. And we're going to use the matrix method for solving it because that's the best and quickest way, especially with three variable systems. All right, so 1, 1, 1, 6. 2, -1, -1, 3, 1, 2, 2, 0. That's my matrix that I'm putting in, 3 by 4. Second matrix, edit, 3 by 4. Negatives, or no, 6, 2, -1, -1, 3, 1, 2, 2, 0. And then the second matrix, math. And then the matrix we get back from RREF, I'll just copy and paste that picture. Is, look at that bottom row. It is a little bit different than the last one. It has a 1 in that last place. What that says is that 0x plus 0y plus 0z is equal to 1. How can 0 plus 0 plus 0 equal 1? It can't. Okay? So what that bottom row tells us is that this is no solution. That's what that row tells us. So the answer to this is no solution or inconsistent would be what we call that. Okay? Takes a little bit of practice, get used to doing this on the calculator and get the routine down, but it's the same every single time. It's not going to change out of that. And just recognizing, always look at the bottom row before you start doing anything just to see if it's infinitely many solutions or no solution. The majority of them are going to have one solution just because that's the most common thing that we want in a math class is for things to have an answer, right? But the no solution and infinitely many solutions tends to come up sometimes. But again, it's in the minority of when it comes up. But it just takes the practice of going through there, and feel free to rewatch the video to get that routine of what order to do things in, or hit up YouTube. There's a ton of videos on how to do this with our calculator. I have to fight my Algebra 2 students off at school when we're doing this because they're masters of Google, and they Google how to do all this stuff before you want them to do it with a calculator. They're like, I got this fancy calculator. I know it'll do this. And they figure it out. All right, last thing in these two sections is this thing that they throw in there. It's just row operations. And it's really just a following directions kind of thing. In my opinion, it's really not unless you're going to be an engineer and you're going to go into that sort of thing. I don't see much need in it. But there are people who take college algebra that are going into engineering, so they do need to know this. So that when they go to their linear algebra class, they can do it. So here is a matrix: 5, 2, 13, -3, 1, -10. It doesn't matter if the matrix they give us for this came from a system of equations or it's just made up. It doesn't matter. This one's just made up, just so you know. All right. And what the row operations says is it'll tell you what row to change, and then it'll tell you how to change that row. So the way that we're going to change row 2 is we're going to take 3 times row 1 plus row 2. But row 2 is the only row that's changing when we get done. So what I always say do is look and see what row is changing. Row 2 is the only one changing. So that means row 1 ain't changing. So I'm going to copy down row 1 before I even start because my rule says row 2 is the one that changes, not row 1. And then I follow the instructions. The instructions are, say, 3 times row 1 and add it to row 2. So what you're going to do is you're going to take 3 and you're going to multiply it times the things in row 1 and add it to the corresponding thing in row 2. So 3 times 5 is 15 plus negative 3, which would be 3 times 5 is 15 plus negative 3. It'd be like minus and 3, so that'd be 12. And then I'm going to take 3 times positive 2. That's 6 plus row 2. 6 plus 1 is 7. And then I would take 3 times 13, which is 39, plus row 2, so plus negative 10, would be 29. That big old thing there is the final answer for that. That you're just following instructions. If they gave you like a list of row operations and they said number 1 is this, number 2 is row 1 is equal to row 1 minus row 2, then you would do that first step, and then the next thing you would do is follow that instruction. So I'm starting from this one. Okay, so that is the answer to this. So we're going to go, okay, well, which one is changing now? Row 1's the one changing. So row 2 doesn't change. 12, 7, 29. So I'm taking row 1 minus row 2, and that answer goes in the place of row 1. So row 1 is 5 minus 12 would be negative 7. 2 minus 7 would be negative 5. 13 minus 29 be negative 16. And then that is the answer to the second operation. If they had a third operation, you'd do it to that answer that's in red. Now, you just follow them in order. It's really just a follow directions type thing. But the key thing that most people make a mistake on that stuff is they will change a row that isn't being changed. Be careful of that. Safeguard is to go ahead and say, okay, if row 2 is changing, I'm going to copy down row 1. If row 1 is the one changing, I'm going to copy down row 2 before I start. That will save you from that because this is too easy to miss. And they always, every year, they've always put at least one of these on the final exam. So that's 2 points that's almost free because it's so easy to do. But you just got to be careful and not change a row because you know good and well that the multiple choice version of it is going to have the easy mistakes that you could make as a choice out of that. So be very careful of that. All right. So row operations, the last thing in those 2 sections out of that. So, all right. The matrix stuff is not going away. We're going to still work in there. So section 12.4 is solely dedicated to matrix operations and algebra. I get kind of excited about this stuff because it's one of my favorite topics. It's one of my favorite courses in undergrad was linear algebra, which was all matrix stuff. There's some neat things that happen once you get to the higher level stuff. It's pretty cool. So I get excited about this stuff. But we're going to do the basic things. We're going to do operations. What are operations in math? Yeah, add, subtract, multiply. Good thing is there's no such thing as division with matrices. It does not exist. Okay, so we're going to add, subtract, and multiply. Show you how to do that. It's really, really easy to do. All right, so let's talk about adding and subtracting. I'll show you how to do this by hand, which is the way I normally do it. But I'll also show you that your calculator can do this really easily as well. So what we're going to have here is we're going to have a matrix, and we're going to call it matrix A. And it's going to be a 3 by 2. So 3, 6, 5, negative 7, and 2, 10. Matrix B is going to be the same size. 1, negative 2, 11, 8, negative 5, 14. And then the third matrix we're going to call matrix C. And it is a 2 by 2. 6, negative 4, 2, negative 1. All right, so we're going to use these three to set up some problems out of our stuff. Now, if I came to a section on a quiz or a test that had this set up and said use these three matrices to do the following problems, I would probably in my calculator go and say, okay, second matrix, and I would put each one of those in for A, B, and C. That's probably what I would do out of that. But I'm going to go ahead and just put in A. Let's just go ahead and put them in there to get the practice. So the first one, matrix A, was a 3 row by 2 column. So 3 by 2, and that's the right size. So I'm going to put the numbers in there: 3, 6, 5, negative 7, 2, and 10. All right. Second, quit. Second matrix, go over to edit. Matrix B is also a 3 by 2. 1, negative 2, 11, 8, negative 5, and 14. Second, quit. Second matrix, over to edit. And matrix C is a 2 by 2 in this case. Hey, it happens to be the right one. I wonder the chances of that. All right, so all that stuff is in there. All right, now I'm going to show you operations here and the rules for operations. So addition and subtraction must be equal dimensions. If they're not equal dimensions, that means rows and columns, then you cannot add and subtract them. That is the rules. So the reason being is if I'm going to do the problem A plus B, I'm going to add the corresponding parts together because they're the same size. A is a 3 by 2, B is a 3 by 2. So they have the exact same same number of rows and columns. So they have matching elements or pieces. So if I'm going to add those, to do it by hand, I just go 3 plus 1. 4, right? And then I go to the next piece, 6 plus negative 2. That's also 4. And then I go to the next row, 5 plus 11, be 16. Negative 7 plus 8, be 1. And then the last row, 2 plus negative 5, negative 3. 10 plus 14 is 24. If I'm unsure of myself, I can go to the calculator and I can tell it second matrix, matrix A plus second matrix, matrix B, and then hit enter, and lo and behold, I get the same answer. I never do matrix addition with the calculator just because it takes me twice as long to type it in as it would to just add the numbers. Okay, because you're just adding corresponding parts. I'm not saying you can't do that. You're welcome to do that if you want to do it that way. I just don't see it being really helpful. Subtraction would be the same way. Let's take B minus A. So it's taking the element in B and subtracting the corresponding element in A. So 1 minus 3 will be negative 2. Negative 2 minus 6, negative 8. 11 minus 5, 6. 8 minus negative 7, double negative makes it plus. So that would be 15. And then negative 5 minus 2 would be negative 7. And then 14 minus 10 would be 4. If I'm not sure myself, go. Second matrix B minus second matrix A. And I get the same answer. The reason that I can add and subtract those is they are the same dimensions. They have the same number of rows and same number of columns. If they do not have the same number of rows and columns, i.e. example C, A plus C, it's called undefined. If you tried to do that with your calculator, you didn't pay attention to the dimensions of it, and you just had them already typed in your calculator, and you were just buzzing through the test, if you go to your calculator and you try to tell it to say second matrix A plus second matrix C and hit enter, it's going to throw back an error that says dimension mismatch. That means they ain't the right size to be able to do that together. Okay, so if you get that back, either you put the matrix in wrong or they really won't work. So that's how it tells you, hey, what's the deal here? So go back and check your matrix sizes to make sure that you've done them correct. And we see A is a 3 by 2 and C is a 2 by 2. So that definitely cannot go together with addition or subtraction. So addition, subtraction, it must be the exact same size for it to be able to be done. Okay, really all there is to the adding and subtracting of matrices. So it's not real hard. All right, the next thing is just extremely difficult. It's called scalar. I'm trying to do my handwriting a little better. Scalar multiplication. It's just, man, it'll wear you out. So let's take a matrix and let's just use that one that we've already got typed in. 3, 6, 5, negative 7, 2, 10. That was the matrix A that we already typed into our calculator. And we're doing scalar multiplication. Scalar multiplication would be an example like negative 3, and then they'll put the name of the matrix beside it. All that means you're doing is you're taking negative 3 and multiplying it by everybody that is in that matrix. It's like distributive property is the way I think about scalar multiplication. Is I think distributive property. You can't call it that, but that's the way your brain wants to work with it. All right, so we're going to multiply every single element by the negative 3, and that's going to give us our solution to that operation. So negative 9, negative 18, negative 15, positive 21, negative 6, negative 30. And there's our solution. Maybe you don't know your multiplication tables quite as well as I do, and that's quite okay. On your calculator, you can just go negative 3, second matrix, pick up the one you want to do that to, and there it punches it out for you. Scalar multiplication, it's distributive property. It's one of those things I normally don't do with the calculator unless there's like fractions involved and I just don't feel like working it out, that sort of thing, or if it's really large numbers and I don't know my multiplication tables for those numbers too well. So just be mindful of that. Now, where I would think the calculator would be handy is when you combine matrix multiplication or matrix addition and subtraction with scalar multiplication. So let's just use the same two A and B that we had earlier. We've already got them in our calculator, so we don't have to take the time to work those in. So if matrix A and matrix B are the same ones we had before, and we do this problem, 2A minus 4B. That means take 2 times matrix A, which I'm going to write it out here, but this is where I might actually use the calculator a little bit. So those are the same two A. This is matrix A, this is matrix B from the first examples that we did. 2 times matrix A minus 4 times matrix B. And I would just do that math. I would do 2 times 3 is 6, 12, 10, negative 14, 4, and 20 minus 4 times 1 is 4, negative 8, 44, 32, negative 20, and 56. And then I do that subtraction. 6 minus 4 is 2. 12 minus negative 8 would be 20. 10 minus 44 would be negative 34. Negative 14 minus 32 would be negative 46. 4 minus negative 20 would be 24. And then 20 minus 56 would be negative 36. And, a lot of, multiplying and then doing the subtraction there, but not just strenuous work involved. So I could do it without a calculator, but when they start combining the scalar multiplication with that, there's a lot of operations in there. There's a lot of chances for just missing a sign. Not that you don't know how to do it. You just could make a silly mistake and forget to write the minus sign. I'm kind of prone to doing that sometimes. So if I put those matrices in my calculator like I have, I could just do 2 second matrix A minus 4 second matrix B and hit enter, and it cranks out that problem for me out of that. So the calculator can handle a lot of things with matrices. Scalar multiplication is definitely one of them that it handles real well. But we could handle scalar multiplication probably on its own without it. But it, like I said, you got the calculator. Let's learn to use that dude. All right. Next thing is something that I actually do recommend that you use the calculator to do, and that's matrix multiplication. Multiplying matrices is a lot more strenuous than the other things that we've done. Multiplying matrices. You've got 2 matrices that you're multiplying together. They have dimensions. So what has to happen is your row of the left matrix and the columns of the left matrix times the row of the right matrix times the columns of the right matrix. What has to happen is these 2 must match. For you to be able to multiply them together, the columns of the left matrix have to be the same number as the rows of the right matrix. What this implies is that matrix multiplication is not commutative. If you did matrix A times matrix B, that is not always the same as matrix B times matrix A. You can't change the order and it gets you the same thing. Sometimes if you change the order, you can't even, it's undefined operation. It doesn't work. Examples of this. All right. So let's take a couple of matrices. So I'm going to call this, we're going to do 2 different ones here. So matrix A is now going to be this matrix, 2, 4, negative 1, 5, 8, 0. And matrix B is going to be this one, 2, 5, 1, 4, 4, 8, 0, 6, negative 3, 1, negative 2, negative 1. Okay. All right. So with these 2, if I ask you to do matrix A times matrix B, what size is matrix A? It's a 2 row by 3 column. Matrix B is what size? 3 rows by 4 columns. So we have a 2 by 3 times a 3 by 4. those numbers in the middle, they match. So that means this is possible. You can do this, okay? So because it's possible, because those numbers match, what I'm going to end up with when I solve it is a 2 by 4. That's what my answer will be, is a 2 by 4 matrix. The outside tells you that. So 2 rows by 4 columns. Now, I used to do these all by hand. I'm a little out of practice because I don't do them by hand as much anymore. But what it basically boils down to is you take the row of the left matrix times the column of the right matrix, just like the way you do the size. So 2 times 2 is 4, plus 4 times 4 is 16, plus -1 times -3. So you'd have 4 plus 16 plus 3 would be 23 would be your first term out of that. That's a blooming lot of operations to deal with, because it's three multiplications and then 2 additions for the first spot. So that's 5 operations for the first spot. And then for the second spot, it's the same thing. It's 3 multiplications, 2 additions. It's 5. And so there are 8 elements in a 2 by 4. So that's actually going to end up being 40 operations that you've got to do that problem if you do it by hand. This is why we're not getting any power. It's not plugged in. I'm like, why is it? That thing's plugged in the whole time. Let's do that. There we go. All right. So doing this by hand, tedious, not extremely hard, but it's long and there's a lot of operations. There's too many ways to mess it up. So I really encourage you, folks in college algebra, to just do this with the calculator. Do the matrix multiplication with the calculator. So I'm going to go and hit second matrix, and I'm going to enter in matrix A. It's a 2 by 3. And I'm going to enter that one in. So 2, 4, -1, 5, 8, 0. Second quit. I'm going to go enter in a new matrix B. And it's 3 by 4. And so it's 2, 5, 1, 4, 4, 8, 0, 6, -3, 1, -2, -1. Oops. Yeah. All right. Make sure I got all that stuff in there right. 2, 4, -3, 5, 8, 1, 1, 0, -2, 4, 6, -1. All right, good deal. And then I'm just going to go second matrix A times second matrix B. And there's that 23 in the first spot that I'd said. And then 41, 4, and 33. And the last row, 42, 89, 5, and 68. If I tried to do example G, matrix B times matrix A, that's going to be a 3 by 4 times a 2 by 3. Those numbers in the middle do not match, and so that's undefined. If you try to do that with your calculator, it would tell you a dimension mismatch error again, just like it did with the addition thing. I went matrix B times matrix A, dimension mismatch. It can't do it because the dimensions don't work. Okay, so matrix multiplication, not normally commutative. There are a few times that it is, but those are pretty special matrices when they are commutative like that. All right. So last thing in this section, last thing of the evening, is using the calculator to find an inverse matrix. Inverse matrix is, it's kind of like a reciprocal, but it's not just straight up flipping everything over. It's a little different because it's a matrix. So let's just take an example, matrix A, and invertible matrices are always square, meaning they have the same number of rows and columns. So if you look at one, they tell you to find the inverse matrix of it, and it doesn't have like a 3 by 3 or a 2 by 2 or a 15 by 15, you know it can't be done. Okay, it's got to be square to be able to be done. So let's pick out a square one. So 1, 1, 0, -1, 3, 4, 0, 4, 3. So this is a 3 by 3. It's a square matrix, is a way they describe that. Just means it's got the same number of rows and same number of columns. The inverse matrix, somebody always asks, well, how do you do this by hand? I know you can just punch it in the calculator and get it, but how you do it by hand? The way you do it by hand is by row operations, and it takes about 1.5 pages of paper per problem to do that. It is not the most friendly thing in the world to do, and we're just kind of checking a box here on the things that we've done with matrices for college algebra. Never do they make you do it by hand, and unless you're going into engineering, you don't need to be able to do it by hand. So we're going to do it with the calculator. So the calculator has a nice inverse button on it. All we've got to be able to do is punch that thing into the calculator as a matrix. So I'm going to go to the calculator. I'm going to go to second matrix. I'm going to go to matrix A and edit that and put a 3 by 3 in there. And I'm going to put 1, 1, 0, -1, 3, 4, 0, 4, 3. Oops. Hit something wrong. Go back over there. That's a 3 there. There we go. All right, got everything in there. Then I'm going to hit second matrix. I'm going to pick the matrix that I want to invert, which is matrix A for me. And then I'm going to use the inverse button, which is just the x to the -1 power button, which is right below the math button. Over here on the left, right below math. Don't hit second, don't hit anything, just hit that button. It'll put the little -1 exponent there, and that's the inverse button. Hit enter. And then I'm going to change that to fractions because I've got mine set to do decimals first. I'm going to hit math, enter, enter. And those become the elements for my inverse matrix. So 7 over 4, 3 over 4, -1. I'm just going to copy and paste that. Write it out. Well, that's one way to do it. All right. So this is the inverse matrix that we're dealing with there. Right? Just being able to find the inverse matrix. Really our job. So almost, well, everything we've done tonight can be done on the graphic calculator with matrices. Everything that we do with these particular sections can. Now next week that's not the case. We've got some inequalities that we've got to do in some non-linear systems, but so we can't do everything in the calculator. But we'll do a good bit of pretty cool stuff with those and try to knock out the rest of the material for the course next week. So